7.2 Coulomb's charge. We're going to examine the forces that exist between two charged particles, like the ones that are shown in the diagram below, Q1 and Q2, that are separated by a distance of r. We know that with charged particles, we should experience an electric force between them, depending on the size of the charge and the sign of the charge, whether they are positive or negative. So Coulomb states that the force between 2 point charges is inversely proportional to the square of the distance between the charges and directly proportional to the product of the charges. This statement is summarized as Coulomb's law and can be expressed as an equation. Electric force is equal to kQ1 times Q2 over r squared, where k is the proportionality constant and k is equal to 8.99 times 10 to the power of 9 newtons times meters squared per Coulomb squared. Now you might note that the structure of Coulomb's law is similar to the equation for Newtonian gravitation, which is g m1 m2 over r squared. This is not just coincidence. There are many similarities between the electric force and gravitational force. We've studied this before in grade 11. We've compared these two forces, and we'll continually talk about how these two are similar throughout this unit. Now let's look at some special properties of Coulomb's law. Including the negative sign for a negatively charged object would imply a direction. You never include the sign of a charge when solving problems related to Coulomb's law. So let's highlight that. When solving problems, we don't include the sign of the charge. Now, the sign of the charge will indicate the direction of the force. So it's something that we will keep in mind, but we don't include when we're doing calculations. The second point that we need to remember is that the magnitude of the electric force is the magnitude of the force exerted on each of the particles. Okay. So what if we have two particles exerting a force on a third one? Well, the total force on this example in Q2, the center particle that is in between Q1 and 2Q1, equals the sum of the forces from both of these charges, both Q1 and 2Q1. And this is based on the principle of superposition, which states that the resultant or net vector acting at a given point equals the sum of the individual vectors from all sources, each calculated at a given point. Let's start taking a look at Coulomb's law with some examples. Sample problem number 1. An early model of the hydrogen atom depicts the electron revolving around the proton, much like the Earth revolves around the sun. The proton and electron both have mass, so they exert a gravitational force upon each other. They also have charge, so they also exert an electric force on each other. The distance between the electron and the proton in a hydrogen atom is 5.3 times 10 to the power of negative 11 meters. The charge on each, both the electron and the proton, is 1.6 times 10 to the power of negative 19 coulombs. Remember, this is the elementary charge. It's positive 1.6 times 10 to the negative 19 if we're talking about protons, and negative 1.6 times 10 to the power of negative 19 coulombs if we're talking about electrons. The mass of the electron is 9.11 times 10 to the power of negative 31 kilograms, and the mass of the proton is significantly larger. It's 1.67 times 10 to the power of negative 27 kilograms. Your job is to calculate the ratio of the electric force to the gravitational force. So let's take a look. Let's find both the electric force and the gravitational force. So to solve for the electric force, we're going to put in Coulomb's constant, 8.99 times 10 to the power of 9 newtons times meters squared per Coulomb squared, times Q1. Now, Q1 is the charge on the electron, and that's 1.6 times 10 to the power of negative 19 coulombs. And the charge Q2 is the charge on the proton, and it too is 1.6 times 10 to the power of negative 19 coulombs. Instead of writing it twice, I'm just going to put squared on top. We'll divide this by the distance between the electron and the proton, and that is 5.3 times 10 to the power of negative 11 meters, and that will be squared. If we punch this in, the electric force between the electron and the proton is 3.6 times 10 to the power of negative 47 newtons. Okay. Oh, I apologize. Correction. It is 8.2 times 10 to the power of negative 8 newtons. I was looking at a different calculation. Hopefully I didn't cause you too much grief. All right, let's find the gravitational force. The gravitational constant is 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared. The mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. The mass of the proton is 1.67 times 10 to the power of negative 27 kilograms, divided by a distance of 5.3 times 10 to the power of negative 11 meters. Don't forget to square it. The gravitational force is 3.6 times 10 to the power of negative 47 newtons. That's what I had written down the first time incorrectly. Okay, so if you know anything about the four fundamental forces of the universe, both electric force and gravitational are among those four fundamental forces. The gravitational force is much weaker than the electric force, and we can see that the gravitational force between these two particles is very, very small, 3.6 times 10 to the power of negative 47 newtons. Well, how many times bigger is the electric force compared to the gravitational force? Well, let's compute this. If you punch this into your calculator, the ratio of electric force to gravitational force for these two products will give you a value of 2.3 times 10 to the power of 39 times greater. Therefore, the electric force between the electron and proton of a hydrogen atom is 2.3 times 10 to the power of 39 times the gravitational force between the same particles. Okay. If we know the electric force and the gravitational force, if these forces were to cause an electron to accelerate, what would the acceleration be for this electron? So we want to find the acceleration caused by the electric force on an electron. We know that the electric force is 8.2 times 10 to the power of negative 8 newtons, and the mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. So the acceleration caused by the electric force would be 9 times 10 to the power of 22 meters per second squared. Let's do the same, this time using the gravitational force. If the gravitational force were to cause the electron to accelerate, we found that the gravitational force was 3.6 times 10 to the power of negative 47 newtons, divided by the mass, which is 9.11 times 10 to the power of negative 31 kilograms. The acceleration caused by the gravitational force would be much smaller. It would be 4.0 times 10 to the power of negative 17 meters per second squared. Perfect. Okay. In sample problem number 2, we have a test charge, Q3, which is balanced in between Q1 and Q2. Q3 is positive, and Q1 is negative, and Q2 is also negative. So this charge Q3 is in equilibrium. We know that the force exerted on it by charge number 1 is equal to the force exerted on it by charge number 2. As a result, it will end up some distance in between the two. We'll call this distance x. Our job is to find x, determine the location of Q3. So since it's in equilibrium, we know that the force, the electric force from Q1 is equal to the electric force by Q2. As a result, Q3 lies in equilibrium. The net force acting on it is 0. It's suspended at that location, x, in between Q1 and Q2. So we can use this statement to solve for x. Now bear with me. I'm going to warn you in advance. This is a tedious question. We can replace this statement with k Q1 Q3 over, and the distance between Q1 and Q3 is x squared. Fe2 is equal to k Q2 Q3 divided by L minus x squared. Our job is to solve for x. Let's start by cleaning up whatever we can here. We have Q and Q3 on both sides of this equation, so we can actually cancel them out. When we do, we are left with Q1 over x squared is equal to Q2 over L minus x all squared. To solve for x, we're going to cross multiply. So we have Q1 L minus x squared equals Q2 x squared. Our next step is to expand this difference of squares. So it's Q1 times L squared minus 2LX plus x squared equals Q2x squared. Now we're going to distribute this Q1 across all three terms. We have Q1 L squared minus Q1 2LX plus Q1 x squared equals Q2 x squared. Okay, we're going to collect like terms and see if we can solve this equation. So we're going to bring everything over. So we're going to have 0 equals Q2 x squared minus Q1 x squared plus Q1 2LX minus Q1 L squared. Okay, now these two terms are both x squared terms, so we're going to factor the x squared. We have Q2 minus Q1 plus Q1 2LX minus Q1 L squared. And let's divide both sides by Q1. Q1 will cancel out here and here. We can simplify this. We are left with 0 equals x squared times Q2 minus Q1 over Q1 plus 2lx minus L squared. Okay, we're going to sub in what values we know. We know Q1, we know Q2, and we know L. So we are left with 0 equals x squared times 1.80 times 10 to the power of negative 5 minus 2.00 times 10 to the power of negative 6 all over 2.00 times 10 to the power of negative 6. I've omitted units just to keep this simple. Plus 2 times L is 4 meters minus 4 meters squared. We can simplify this. We are left with 0 equals 8x squared plus 8x minus 16. Thankfully, the gods of math and physics are on our side, and this is rearranged into a simple quadratic equation. Let's reduce this, dividing everything by 8. So we are left with 0 equals x squared plus x minus 2. Now this is a simple quadratic equation that can be factored. The factors are x minus 1 and x plus 2 equals 0. So we know x is equal to 1 or x is equal to negative 2. We're going to reject the negative sign. So our value of x is 1 meter. Therefore, the location of Q3 is such that the electric forces from 3Q1 and Q2 cancel is 1 meter, or 1 meter to the right of Q1. Okay, let's try a similar example, this time in 2 dimensions. So we have Q2, which is in between Q1 and negative Q1. So Q1 is positive and negative Q1 is negative. Notice the symmetry in this diagram, and that symmetry is going to allow us to simplify this equation a little bit. Q1 and Q2 are a distance r from each other. And r is the hypotenuse of a right-angled triangle whose sides are 4 meters and 3 meters. So we can actually calculate r. It's equal to the square root of 4 squared plus 3 squared. So r, if you solve that, is equal to 5 meters. Perfect. I'm going to make up positive and right positive. Our first step is to calculate the force of Q1 on Q2. So FE1 equals KQ1 Q2 over R squared. K is 8.99 times 10 to the power of 9 newtons times meters squared per Coulomb squared. Q1 is 5 times 10 to the power of negative 6. And I apologize, it may not look like that on my note, but I believe you have the updated note with the correction. It's negative 6, negative 6. Okay. And Q2 is 1 times 10 to the power of negative 6. We just calculated the distance between them. We said it was 5 meters. So Fe1 is 1.8 times 10 to the power of negative 3 newtons. Okay. Now notice the symmetry. Negative Q1 is the same distance, 5 meters from Q2. It also has the same magnitude of charge. So the magnitude of negative Q1 is also 5 times 10 to the power of negative 6. The only difference is that the force, since this is positively charged and this is positively charged, will be in this direction for Q1 and Q2. And since Q2 is positive and negative Q1 is negative, Q2 will be pushed in this direction. Okay, let's calculate the force. Fe2, that's negative Q1 on Q2. Since they are symmetrical, and since we ignore the sign when finding the magnitude of the electric force, we know that Fe2 is equal to Fe1 and is equal to 1.8 times 10 to the power of negative 3 newtons. Okay. Now, in order to find the net force, we have to find the x and y components of Fe1 and Fe2 in order to find the net force acting on Q2. So step 3 is to find the x component of Fe1. If we're looking, that will be this vector right here. We'll label it Fe1x. So we know that Fe1x, which is the opposite to the angle theta, and Fei would be the hypotenuse. Opposite hypotenuse is the trigonometric ratio cos theta. So Fe1x is equal to Fei cos theta. And just so that we know, cos theta is equal to opposite over hypotenuse. So we can rewrite this as Fei, we said, is 1.8 times 10 to the power of negative 3 newtons. The opposite is 3 meters. And the adjacent, or the hypotenuse rather, is 5 meters. So 3 over 5 is equal to cos theta. If we punch this into our calculator, we get the x component is 1.1 times 10 to the power of negative 3 newtons to the right. Okay. Now let's find the x component of Fe2. So what we're finding is this component, Fe2. Fe2x. By symmetry, we can see that the magnitude of this will be the same, but the direction will be opposite because we're dealing with one positive charge and one negative charge. So we can state by symmetry Fe2x equals Fe1x, but opposite directions. So Fe2x is 1.1 times 10 to the power of negative 3 newtons. This time, left. So let's find the net electric force in the x direction. It's equal to Fe1x plus Fe2x. That's plus 1.1 times 10 to the power of negative 3 newtons plus negative 1.1 times 10 to the power of negative 3 newtons. So the net force, the net electric force in the x direction is 0. Okay, now this is not the end of the question, and I apologize that I haven't given you enough space, but let's carry on. I'm going to add a page here. I haven't added it in the right direction. Just give me a moment. Okay, so we found the net force in the x direction. Our next step is to find the y component. Y component of Fe1, and then we'll find the y component of Fe2. So, finding x and y components, if you found the x component, it's easy to find the y component. So finding Fe1y is equal to Fe1 sine theta. So the x component was Fe1 cos theta, the y component will be the opposite, Fe1 sine theta. We know Fe1 is 1.8 times 10 to the power of negative 3 newtons, and sine theta is equal to adjacent over hypotenuse. And if we take a look back at our diagram, the adjacent, what we're finding is this component here. The adjacent is 4 meters and the hypotenuse is 5 meters. So sine theta is 4 over 5. Punch it into our calculator, and FEI is 1.4 times 10 to the power of negative 3 newtons, and it's directed down. Good. Let's find the y component. Of Fe2. Fe2y equals Fe2 sine theta. Now just to show you on the diagram, this is also pointing in the downward direction. Because again, we have a positive charge and a negative charge, so it will be directed in this direction, downward. So the y component is pointing down. So we can solve. That's the same as above. So it's 1.8 times 10 to the power of negative 3 newtons times 4 over 5. F E2y is actually equal to Fe1y, which is 1.4 times 10 to the power of negative 3 newtons. And this time it's in the same direction as well. So we can find the net electric force in the y direction. It's equal to Fe1y plus Fe2y, which is 1.4, negative 1.4 times 10 to the power of negative 3 newtons plus negative 1.4 times 10 to the power of negative 3 newtons. If we punch this in, we get negative 2.8 times 10 to the power of negative 3 newtons, or 2.8 times 10 to the power of negative 3 newtons down. And that, my friends, is equal to the total force acting on Q2. Since the x components cancel out, the net force is equal to the net y force, and we can state, therefore, the net electric force acting on Q2 is 2.8 times 10 to the power of negative 3 newtons down. All right, I've assigned practice problems on page 332. Numbers 1 to 3, and review page 333, numbers 1 to 10. Have fun.